The statement for the question is, an undirected graph G, V, E contains n where n is greater than 2 nodes named V1 to Vn. Two nodes Vi and Vj are connected if and only if the difference between I and j is less than or equal to 2. Each edge Vi, Vj is assigned a weight I plus j. A sample graph with n equal to 4 is shown below. Here you see that there is no edge between V1 and V4 because 4 minus 1 is 3. It should be less than or equal to 2 for an edge to be between them. And you can see that the weights are I plus j. For example, the weight of the edge between V1 and V2 is 1 plus 2. V1 and V3 is 1 plus 3. V3 and V2 is 3 plus 2 and so on. So this is the graph for the given problem. So the question is, what will be the cost of the minimum spanning tree of such a graph with n nodes? To solve this problem, we can go ahead from n equal to 3 and see which equation of these 4 equations satisfies for lot of n. 3, 4, you can take a random number of n's and check. So if you take n equal to 3, the graph which satisfies the given statement will be 2 minus 1 is less than or equal to 2. Therefore, there will be an edge and the weight will be 2 plus 1, which is 3. 3 minus 1 is less than or equal to 2. So, there will be an edge and the weight is 3 plus 1, which is equal to 4. Similarly, 3 minus 2 is less than or equal to 2. There will be an edge and the weight is 3 plus 2. So, this is the graph where n equal to 3. This is the graph where n equal to 4. So, for this graph, the minimum spanning tree will be using Kruskal's algorithm. We can easily find the minimum spanning tree where first the edges are undiscoverable and you take the most minimum among the weights and add that edge. So 3. The next most minimum is 4. Now all the nodes have been discovered. So this is the minimum spanning tree. So what is the cost of the minimum spanning tree of this graph? It's 7. So we have to check for these 4 equations if it satisfies this. You put n equal to 3 here, it becomes option A becomes 1 by 12 into, so option A is 1 by 12 into 11 into 3 squared, which is 99, minus 5n, which is 15, 5 into 3. So this becomes 84 by 12, which is 7. So option A satisfies for this. Option B is 3 squared 9 minus 3 plus 1, which is 7 again. So option B also satisfies. Option C is 6n minus 11, which is 18 minus 11, which is again 7. Option C also satisfies. Option D is 2n plus 1, 2 into 3 plus 1, which is again 7. So we see that for n equal to 3, all the 4 equations satisfy. So we have to increase n by 1 and check. So for n equal to 4, the graph is this. So we need to form the minimum spanning tree of this graph. So to form the minimum spanning tree of this graph, we take V1, V2, V3, V4. Now we put the minimum edge first, so it's 3. Then we add 4. The next minimum edge is 5, but if we add 5, a cycle is formed. By the definition of a tree, it's an acyclic connected graph, so we shouldn't add 5. The next smallest is 6. So the cost of this tree is 6 plus 4 plus 3, which is equal to 13. So now again, we'll substitute n equal to 4 in these equations and see which satisfies. So basically this is elimination of choices. So now n is 4. So it becomes, option A becomes 1 by 12 into 11 into 16 is 176 minus 5 into 4, which is 20. This is equal to 1 by 12 into 156. That is 13. So option A satisfies. Option B is 16 minus 4 plus 1. N is 4. So 16 minus 4 plus 1 is 13. B also satisfies. Option C is 6 into 4, 24 minus 11, which is again 13. Option C also satisfies. Option D is 2n plus 1, 2 into 4, 8 plus 1 is 9. So option D does not satisfy. So we know that option D is not the answer. Now to eliminate between A, B and C, we increase n by 1. For n equal to 5, this is the graph. We see that there is no edge between 5 and 1 or 5 and 2 because I minus j, modulus of I minus j is greater than 2. So we will form the minimum spanning tree out of this. So we first add 3. The next smallest is 4, we add 4. The next smallest is 5, but we cannot add 5 because it forms a cycle. The next smallest is 6. We still need to keep adding because V5 is still not discovered. The next smallest is 7, but it forms a cycle, so don't add it. The next smallest is 8, so add it. So the cost of this tree is 4 plus 3, 7, 7 plus 6, 13, 13 plus 8 is 21. So the cost is 21. So we substitute n equal to 5 in these options A, B and C and check. So A becomes 1 by 12 into 11 into 25 minus 25, 5 into 5, which is equal to 1 by 12 into 25 into 11 minus 1, which is 25 into 10. So this becomes 250 by 12, which is 125 by 6, which is not a whole number. So we know that definitely option A is not the right answer. So we eliminate option A. Next, we substitute in option B. Option B is 5 squared minus 5 plus 1, which is 25 minus 5 plus 1, which is equal to 21. So option B satisfies. Option C is 6 into 5, which is 30 minus 11, which is 19. So option C does not satisfy the cost of the tree. So we see that option B is the only one that satisfies for n equal to 3, 4 and 5. We see that D, C and A fail for various n's. So option B is the right answer. So the cost of the minimum spanning tree of a graph, of such a graph with n nodes, is n squared minus n plus 1. The question is, the length of the path from V6 to V7 in the minimum spanning tree of the previous question with n equal to 10 is option A 11, option B 25, option C 31 and option D 43. Now for n equal to 10, we see that the graph is this. Basically the graph will have an edge if between Vi and Vj if modulus of I minus j is less than or equal to 2. So basically, for example, if we take V5, it will be connected to V3, V4 and V6, V7 also. So, and the weights are I plus j for an edge between Vi and Vj. So we have drawn that and we have created the minimum spanning tree out of it. Basically you add from the smallest weight, so you add 3, then you add 4, then you won't add 5 because it forms a cycle, then you add 6, then you won't add 7 because it forms a cycle, then add 8. Similarly, you keep adding alternate edges because the other alternate edge will form a cycle. So you add 8, 10, 12, 14, 16 and 18. So this is the minimum spanning tree. The question is, what is the length of the path from V6 to V7 in this minimum spanning tree? So we come here, we start from V6. Since it's a tree, there is only one path between any two nodes. So we start from V6, V6 to V4, to V2, to V1, to V3, to V5 and to V7. That is the path. So the length of the path is 10 plus V4 to V2 is 6 plus V2 to V1 is 3 plus V1 to V3 is 4 plus V3 to V5 is 8 plus V5 to V7 is 12. So the length of the path is 10 plus 6, 16 plus 3, 19 plus 4, 23 plus 8, 31 plus 12, 43. So the length of the path between V6 to V7 in such a graph with n equal to 10 is 43. Therefore, option D 43 is the right answer.